Hello, welcome to another lesson on probability. This is the first day of 6.3. Um, we're going to start by just going over the rules of probability that we learned earlier. The first one is any probability of any event has to be between 0 and 1. The probability of the entire sample space will equal 1. The addition rule for disjoint events, this is that if there's nothing in common in the two events, the probability of A plus the probability of B will be the probability of A or B. The complement rule is the probability of A complement, so the probability that A does not occur is 1 minus the probability that it does occur. And the multiplication rule is if A and B are independent events, then the probability of A and B is the probability of A times the probability of B. Now we're going to go in deeper in understanding what unions are. Union is any collection of events of let's try that again. The union of any collection of events is the event that at least one of the collection occurs. So if I wanted to shade the union of A and B, so I have event A, event B, A union B is how we write it, and how we draw it. Say if this is A and this is B, we shade everything in A, and then we shade everything in B. This represents A union B. Now if I want to shade the union of A, B, and C, I have 1, 2, 3, and this is A, B, and C. If I make my box around here, I shade everything in A, everything in B, and everything in C. If I shade the union of A, B, and C complement, I have A, I have B, and I have C here. So here's A, B, and C. I'll make a sample space. So everything in A is going to be colored in. Everything in B is also going to be colored in. And everything in C complement, so that's everything outside of C, will be colored in. I guess I could have made my box a little smaller. So everything except for this section, oops, can't color that in. Everything except for this section will be colored in the union of A, B, and C complement. And how I write that is the union of A, B, and C complement. All right, now what's the union of A complement and B complement? So here we only have two sets, A and B. First thing I'm going to do is shade everything outside of A. Because that's what A complement is. And then B complement is everything outside of B, so that just covers that. So this is everything except for space in the middle. Now the intersection of any collection of events is the event that all of the events occur. So if I wanted to find the intersection of A and B, so that's probably that A occurs and B occurs, that will just be this section right here. We write that as A intersection B. Shade the intersections of A, B, and C. So if this is A, B, and C, the intersection of all three of them will be right here. And we write that as A intersection B intersection C. Shade the intersections of A and B complement. So here's A, here's B, Here's my Venn diagram. So you get A and B. So it has to be inside of A, but it has to be outside of B. So if it's inside of A and outside of B, it has to be everything here, but not in the middle. So this is the intersection of A and B complement. Shade the intersection of A complement, B complement, and C complement. So if I have A, B, C, so it has to be outside of A, outside of B, and outside of C. So that will look something like this. Everything that's outside of all of them. All right, now there's an additional rule for disjoint events with 3 events, and it's the same as if there were 2 events. Here we just have to add the probability of C. So the probability that A, B, or C occur if they're disjoint is each of their probabilities added together. Now, the difference between independent events and disjoint events. Disjoint events are events like this. There's nothing in common in the two. Independent events can be disjoint, and they can also have something overlapping. So they're not related in that manner. Independent just means that um, each outcome doesn't depend on previous outcomes. Does not depend on previous outcomes. Just like when you flip a coin, the next time you flip a coin, it doesn't depend on what the coin got the first time. So these are two completely different ideas, and a lot of people uh, get their definitions flipped around. All right, here's a pretty big rule. General addition rule for unions of 2 events. The probability of A or B is the probability A plus the probability of B minus the probability A and B. Or we can substitute the word or for union and for intersection and write this formula. Now this works in any event. Remember, if it was disjoint, it would just be these two because this would equal 0. Uh, but these equations work for uh, all events A and B. All right, now I'll explain how to use that formula in this problem, but I'm actually going to show you 3 different ways to do it. Oscar and Charlie received shots. These are my 2 kids. They received shots at 2 months when they're 2 months old. The doctor said that independently, each one has a 20% chance of getting a fever the following day. So we want to find all the different probabilities for these kids. First thing we have to do is define the events. Event A is Oscar gets a fever. Event B, Charlie gets a fever. What are these events disjoint? Can both of them get a fever? Yes, they can both get a fever, so these are not disjoint events. Are they independent? Well, the doctor said that they are independent. Since they have similar genetics, you could say that they're genetically predisposed, but as far as the doctor's concerned, um, these events are independent. So let's start by drawing a Venn diagram for this situation. So we have Oscar over here, Charlie over here. The probability, so I'll put a little O, a little C there. The probability that they both get a fever is going to be, since these are independent, we can do 0.2 times 0.2, which is 0.04. So 0.04 is going to be the probability that both of them get a fever. Now, since Oscar's whole circle will add up to 0.2, this probability plus this probability have to equal 0.2. So that's going to be 0.16. And the same is going to be for Charlie. So this right here is the probability that Oscar gets sick, but Charlie doesn't. And this is going to be the probability that Charlie gets sick and Oscar doesn't. So the next thing we have to do is find the probability that neither gets sick. That's 0.16. First we have to add up all the probabilities. So 0.16 plus 0.16 plus 0.04 is 0.36. So if I take 1 minus that number, I'll get what it's going to be on the outside, 0.64. That's the probability that neither get a fever. So if I wanted to find the probability of A union B in this situation, A union B would be all three of these numbers added up, which would be 0.16 times 0.04 or plus 0.04 plus 0.16, which is 0.36. Now, if I wanted to use a different method than the Venn diagram, another method for finding this would be find the probability of A union B just using algebra. The previous thing said we could say probability of A times probability of B minus the probability of A intersection B. Now the probability of A intersection B is the two multiplied together, which is 0.04. So I'd take 0.2 plus probability of B, which is 0.2, and I'd subtract out 0.04. 0.2 times 0.2 plus 0.2 is 0.4, subtract 0.04, and I get 0.36. And I have two methods for solving this. My third method is using a tree diagram. In a tree diagram, I could say this is the probability Oscar gets sick, probability that Oscar doesn't get sick. And then I can do Charlie. Charlie and Charlie doesn't get sick, Charlie and Charlie doesn't get sick. Now the probability he gets sick is 0.2, so the probability he doesn't get sick is 0.8. And those are the same probabilities with Charlie. And now when I multiply these across, the probability that they both get sick is going to be 0.04. The probability that just Oscar gets sick is going to be 0.2 times 0.8, which is 0.16. Probability Oscar doesn't but Charlie does, that's again another 0.16. And Oscar doesn't and Charlie doesn't, that's 0.8 times 0.8, which is 0.64. And that gives you more probabilities. So these are three different ways to do the same problem. All right, here's a different type of problem. Just slightly, but Deb and Matt are looking for a promotion at a law firm. Deb thinks that she has a 0.7 chance of getting a promotion, and Matt has a 0.5 chance of getting the same promotion. She also estimates the probability that they both get a promotion is 0.3. What's the probability that neither of them get a promotion? Well, first let's look at the probabilities using a Venn diagram. So in my Venn diagram here, the probability that they both get a promotion is 0.3, so that goes in the middle. Now say if this is Deb and this is Matt, Deb's whole circle adds up to 0.7. So the probability that she gets a promotion and Matt doesn't is going to be 0.4, because that whole thing has to add up to 0.7. And the probability that Matt gets a promotion and she doesn't is going to be 0.2, because his has to add up to 0.5. So now if we add all of these up, 0.4 times 0.3, that's 0.7, that's 0.9. So outside is going to be 0.1. So the probability that neither of them get a promotion is going to be 0.1. Now notice how this is 0.7 and this is 0.5, but the middle isn't 0.35. You can't just multiply those together. The reason for this is that these are not independent. So this is my next question. Why can't we use this rule? These aren't independent. Now, independent, weird N there, and ND. I just screwed up writing that all together. Let me try that again. Independent. All right. Now, they're not independent because if they're both going for the same promotion, if she gets the promotion, that lowers his probability of getting the promotion. And likewise, when he gets the promotion, that lowers her probability. So one probability changes one event changes the probability of other events from occurring. Now, we can also fill out a table to look at these probabilities. The probability that that neither of them get promoted, we said was 0.1. Now I forgot these other probabilities. The probability they both get promoted is 0.3. Matt's promoted and Deb's promoted. The probability that Deb is promoted but Matt isn't is 0.4. And the probability that, oh, that's switched around. That Deb's promoted and Matt is not. The probability that Deb's not promoted and Matt is 0.2. Now when we add these up, it's going to be 0.5 and 0.5. This one is 0.7 and 0.3. And notice that each of these rows and columns adds up to 1, like it should, because all of the events in a sample space should add up to 1. All right, and here's your homework. Good luck.